Hello, I'm Chris Athanas. I'm a KMP developer, and I'm going to be continuing my series on how to program from the ground up. And tech support should be out. I think they contacted me and said they're going to come out on Tuesday to close that dang portal up. Anyway, so we're going into the mighty microprocessor. Like, it's mighty because it kind of like made the whole microcomputer and computer revolution just blew up. Because before that, it was extremely niche activity. Just people weren't that interested because all this stuff was ultra expensive. You couldn't really do too much with it. There was not a lot of information. You had basically be at a university or in industry, but usually defense industry. So anyway, so in 71, this thing came out. Look at all those pins. We'll get into why there's so many pins on this thing, but they only do one little tiny little thing. I'm not doing like 50 things. They're like doing one thing. And they're like one very specific, very specialized thing to do one thing. That's just, 1 or 0. That's all it is. It's not like there's, a radio chip in here or something like that. So let's see what they're made of. Let's go zoom in on one. Okay, wait, let's rewind this thing. Go. All right. Come on. There we go. Finally. Speed it up a little. This is the CPU from some computer. Let's go a little faster. Come on. Yeah, we get it. We're going on the chip, guys. Okay, it's going slowly closer. I guess I need to edit. All right, so we're getting a little closer here. Those are all these little lines all hooked up into each one of those pins on the outside. And this one has a lot more than that, but that's what those are. And those go into these gates, into these all transistors. It's just transistors down here, and that's all how they're all wired up. There's the wires connecting them up. That's all it is. It's nothing magic. And the actual transistor is way down. And here's the wires hooking up into the actual transistor, which is right there. It's like, what? Right in here. Yeah, it's like that thing right there is the transistor. That's where all the stuff comes together to do the stuff, to do the interactions. Let's go looking again.
Today, we are looking at an Intel 486 processor. The CPU was introduced in 1985 at a price of $950. In exchange for your hard-earned wages, you received a hefty piece of ceramic studded with tiny gold pins.
Those are all the pins. So instead of just having them all lined up on the side like the first microprocessor, they had so many they had to do like a grid. So it was all hooked up to that same still piece of silicon.
If you were to remove the protective metal cover, as we are today, you'd find a sliver of silicon no larger than a postage stamp. And on that wafer, over 1 million tiny transistors. When viewed with a normal optical microscope, you can see a vast array of lines snaking across the wafer. These are aluminum interconnects, microscale wires that serve as a global highway to information and power flowing across the wafer. In between the aluminum are splashes of vibrant color. This is light diffracting off the surface of the wafer, or rather, diffracting off the complicated stack of silicon, oxides, and thin metal films. Together, these layers diffract light into a rainbow of colors that you see. Along the periphery are blobs of gold attached to delicate bonding wires. These serve to move data and power onto and off the silicon.
Yeah, that's it.
Communicating.
Those are all the wires. Those are the wires.
World.
Hooked it up. Let's make them.
We can use a different instrument, an atomic force microscope.
Yeah, this is down here is the stuff. Those the wires, and they are like going through different layers. They have the via. They call them the vias. And it's just a wire going through all the layers and hooking up all the different.
To understand
wires.
how tall these aluminum interconnects really are, this instrument scans a tiny probe across the surface, collecting height information, which can be converted into a three-dimensional model. From this data, we can see that the features are only about 2 microns tall and about 4 microns wide. Popular science media likes to use the width of a human hair as a size comparison, but at around 80 microns, I'm afraid we are well past that being a useful metric. A human hair is just too large in comparison to these features. A more appropriate metric would be the size of a bacteria, which are just a few microns wide. Earlier, I mentioned that integrated chips are stacked in multiple layers. If we move over to the scanning electron microscope, we can begin to see some of that structure. You might notice that the underlying layers influence those above it. The surface is wavy, where one...
Yeah, it's like puffy. Because the way they lay it down is they basically make a cloud of smoke, and the smoke sticks to some of it sticks to the next layers up. And that's how they form it. So some of the ones where they don't have the stuff, that stuff doesn't get there, so it gets like bulged out. It's so crazy.
One trace passes over the other. This seems counterintuitive. You'd expect the surface of a precision device like a silicon wafer to be ultra flat. But in reality, as layers are deposited one on top of the other, the surface becomes increasingly rough, as each subsequent layer distorts the surface a little bit more.
Oh, so wild. Like, just, that's none of this is by hand. It's all laid out by computer, of course. They've adjusted things by hand, of course. But like, look at all the wires. It's like so intense.
Modern chips deal with this by polishing the surface periodically throughout the fabrication
It's
process.
just like, and that's all still
But
done
older
with
chips did not require this as much, as they're
photographic processors. Same stuff, just layer.
a lot less complicated. The small circles you see scattered around are vias, vertical plugs of metal that connect different layers together. And while all the features feel very geometric and mechanical, once you zoom in enough, everything is slightly rounded and surprisingly organic feeling. The truth of the matter is that it's just hard to manufacture precise right angles at the scale, and everything starts to get a bit rounded. We can switch to a different detector on the scanning electron microscope that allows us to peer beneath the surface a little better. This allows us to see and map the underlying layers in better detail. The 486 only has a handful of layers, but
I'll let you watch the rest of that. Yeah, so that's what's inside here. And it's just all a bunch of those same components, all these things, all just a whole bunch of them. Using the same technology, using this, the same stuff the same techniques that this guy developed. He used the Mac Daddy. He just said, hey, we can use that stuff instead. And I'm like, okay, let's do that. Okay, so here's like what's going on the inside. This is kind of a cool little animation. I'm gonna like skip through a little bit.
The CPU, short for
but you should go watch the whole thing.
Central Processing Unit, is like the brain of the computer, and once you understand how it works, you'll understand the computer.
I hate that analogy, the brain. No, it's just the way all the calculation happens. It's stepping from program to this, as it steps through the program counter, bringing the instruction in, decoding the instruction, actually doing whatever it is, which is not thinking. It's just somebody's clever plan. That was the reason why the CPU blew up, is because putting all that stuff together is so crazy. It was always available when they had the digital chips. As soon as the digital chips were available, you could have made a whole big computer, and people did. And it was nuts because everyone did them all differently. All the CPUs were all done differently. It was so crazy. Nothing compatible. Nothing. It was like everything's proprietary. So the CPUs like standardized the whole. Like, oh, now we have a CPU that will be standardized. We don't have to reinvent the wheel 1,000 times. Now we can just use that. Oh, that's why it was so.
Let's remove the cover of the CPU and zoom in to see what happens inside. There are lots of different wires carrying information around the CPU. This particular CPU is called the 6502 and was used in computers like the Apple II and the Commodore 64, as well as in the original Nintendo Entertainment System. This simulation of the 6502 can be found online at visual6502.org.
Yeah, that is pretty cool to watch it like clunk through the instruction set.
In every CPU, there is a particular wire that turns on and off at a steady rate to help keep everything in sync. That wire is called the clock, and the clock in this simulation is turning on about twice a second. Modern CPUs are measured in gigahertz, giga meaning billion, and hertz meaning times per second. So the clock in modern CPUs turns on several billion times per second. That speed is what allows CPUs to do very complicated things very quickly. And put the cover back on that today on Scott. The design of the Scott CPU book that goes through each of the components in the CPU very slowly without using a lot of over and look underneath.
When I see it look useful. If it's this level of stuff,
you'll see a lot of motherboard allows all the components.
Yeah, here's the motherboard, here's the CPU socket, and the control bus, the data lines, and everything like that.
It's in the computer to connect to each other. So we'll flip the CPU back over and plug it into the motherboard. On the right of the motherboard is a place for something called RAM. RAM is short for random access memory, and it just contains all the data that is being processed by the CPU. Let's learn a little bit more about RAM by looking at how the CPU and RAM interact. For now, we'll remove the wires on the left and move the motherboard over to make room for the RAM chip. RAM consists of a list of addresses, and at each of those addresses is a piece of data. The CPU normally requests and processes each piece of data from RAM in order, one after the other. However, if the CPU is instructed to pull data out of order, it can do so. That is why it's called random access memory. The data can be accessed randomly if it needs to be, although normally it's accessed in order. When the computer first starts running a program, it's
just step by step. Like if there's no jump instruction, it's going to go from one instruction to the next. Random access means it'll just jump around. It doesn't have to be one after the other like a piece of tape, because there was a time where only the tape was sequential access, not random access. So they had to make it different. So
sends an address to RAM to begin retrieving that program. The RAM address just consists of a series of ones and zeros representing on and off wires. RAM doesn't do anything with that address though until the CPU also turns on the set or the enable wire. If the enable wire is turned on, RAM automatically sends whatever piece of data is at that address back to the CPU. That data is then processed by the CPU accordingly. Once the CPU is finished processing that piece of data, it then sends another address to RAM, turns on the enable wire, and gets the next piece of data from RAM. This process happens over and over again inside the computer. If the CPU needs to save data to RAM, it outputs an address, outputs some data, and then turns on the set wire. The RAM will then overwrite the data at that address with the new data. But what is that data inside RAM? Because it just looks like a bunch of ones and zeros. Well, it's made up of different things. Some of the most important pieces of data in RAM are the instructions. Instructions just tell the CPU to do different things. There are also numbers inside that data. These are numbers that you might want to add together, compare, or simply process in some way. Another thing, and this is kind of weird, that is in the data is addresses. Particular memory addresses in RAM, the data itself is also an address. These addresses can be used for various things. For instance, if you want to output a number to an external device, you have to know the address of that particular device. Do you want to send data to the printer, or do you want to send it to the monitor, for instance? There are also letters stored in RAM. If you want to show some text on the screen, you would actually store it as a bunch of ones and zeros in RAM. Each letter is stored as a particular combination of ones and zeros according to a character code. These character codes are arbitrary. Someone just decided that this is a lowercase a, and this is an uppercase G, for instance.
Well, we'll get into why they did it in certain ways. There wasn't completely arbitrary. There were once they became a standardized, it became a standard. But in the beginning when all computers started, yeah, it was completely arbitrary. People did their own systems. That's why all this stuff was completely incompatible. A one could be an A one could be a Z. It's just.
So that's what's actually in the data inside RAM. Now let's go back to seeing the data as just a bunch of ones and zeros. We'll now move the RAM chip into the RAM socket on the motherboard. We'll then group the RAM addresses and data together, pull the CPU out of the motherboard, and look at what's called the instruction set of the CPU. As we saw earlier, some of the pieces of data in RAM are instructions, and each CPU has its own set of instructions that it understands. So there might be a load instruction, which loads a number from RAM into the CPU. After a couple of these load instructions, there might be
we'll be going through all those. Yeah, just they have so as each instruction is taken off, it converts it to this command, which says, oh, I should load a number. What number into the CPU? Well, which number? Well, it'll have some other number either right there in memory or the address of some place that get the number
an external
from.
Device like a monitor here consists of things like instructions, numbers, addresses, into the has to begin on. So
Got a good animation here.
Unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison, like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other.
Well, that's kind of giving an answer, guy. So yeah, it does do an answer. It might not be to like a number. It might be just like if you're comparing two values, whether they're equal and one's greater than, one's less than, it'll set a flag someplace in a register someplace. So it is. That's a little
For this, the ALU uses what are called flags, and they help the control unit.
Okay, so he says flags. So it is an output. Flags are an output.
Decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily.
Well, there's, you have the registers for values, stuff like adding things together, subtracting, whatever. And then you have flag register. They're both registers. Just numbers. just binary digits in there. There's no magic. It's still just ones and zeros.
Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while in.
I've heard, when I first had this explained to me, they made it sound like this was such a magical thing. And it's just like, are you serious? We'll get into why it's just like, all right, okay, it's just clever. It's clever, but it's nothing magic. There's zero magic.
Instructions being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit...
Remember how that flip-flop has that same set reset thing? It's that same kind of thing going on under the hood here. Same stuff.
Turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer.
Yeah, it's just a wire. One wire, two threads. That's all these wires are all hooked together. That's all. Still just wires, just hooked together.
On the bus are some other registers with their own set.
Yeah, these are just things holding numbers. Same thing holding numbers. Same thing, just another place to hold some numbers. Okay. This is all very clever arrangement.
Enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire.
Now, this is a bad diagram here because there's only got one connected wire. Only one connected wire here. These wires are not connected together. It's only this wire, this wire, this wire, like this T. And these are not connected together at all. So this is a kind of a bad diagram a little bit, but it needs to have little dots here to say this is actually connected. Even though these aren't on, he's got the on-off thing correct. But yeah, because it's being supplied. So the output here is going to go all the way around here. So that's correct. But he should have these dots. So that's one
of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus.
Yeah, these are just called buffers. I call them buffers. It just holds the value. It's like a little piece of RAM, a little piece of memory. Okay, it's just more of that stuff.
So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU. And
well, in the 6502 or his thing, it kind of is how it works. But other CPUs go totally different. They'll have like dozens of these things all over the place for caching and for optimizing their operations. It's like it's intense. The modern computer CPUs are crazy. They have to be. They're all written. They're by code. Absolutely have to be written by code. You cannot do these by hand anymore.
Ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With a compare instruction, we're not interested in the number that is output by the ALU.
So it's just putting a little code on the wire. It says, hey, do this one. Hey, we'll show how one of the ALUs, there's like different operations the ALU can do. It's like it can add, it can subtract, it can compare. And this is what it's telling it. This is the actual people, and the thing in charge of like sequencing through all the stuff, which if you want to know how all that stuff actually works, Ben Eater goes and breaks it all down to how all that stuff works. But basically it figures out what the instruction is, and then it tells the ALU if the ALU is involved in that instruction, lets it know what it is with this for these three digits, 3 bits. Just let it know, because it doesn't have a lot of instructions. But other CPUs will have more lines because it'll be like more different things that the ALU can do.
We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B.
So it's just a bit, it turns on. That after an operation happens in here, it sets a bit here. And that's all that's happening.
The inputs are the same, then the equal flag turns on. And if both of these
flag is the same as a bit. Bit, flag, bit, same thing. I don't know why they use this terminology. They had to switch it around, but okay, this is what they do. All right, fine.
Are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction.
I guess they use the word flag to mean like semaphore, the old semaphores they had before all computers. So like you'd set some flag to see for some condition, or a ship. I guess it was like maybe ship code, because there's a lot of stuff that's coming through the Navy. So maybe that's what they're talking about there. But it just means an indicator, Like, in sports, when you have red flag, there's a red flag on the floor. It's a red flag on the field. It's like, oh, okay, that means there's some condition that just happened. So I guess that's where they're getting the flag. But that means we're using this as an indicator. And that's kind of what a flag is.
So we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than
that's how it does the loops.
One possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus.
That's how it does the jumps for looping around. That's how it changes the address back to another to the location memory to do a loop. We'll get into that.
Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM, since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from...
And all a jump is, they make it sound like it's such a big deal. They just put a new address with the instruction pointer, which we'll get into, I think, in this next video. We'll get into the instruction pointer, and that's what just sets the next instruction address to some other place for this to pick up the next. It's a boo a jump. It's just setting the address to another location. Instead of it being the next location, it's going to just address +1 for the next instruction. It like sets the address to some other place. The instruction pointer to some other place in memory. That's it. And they said that's a jump. Okay, whatever.
From it and moves
Let's go here
through the same 6-step checklist for every instruction and uses the clock to stay on pace. The first item on the checklist says to make a note of the number.
This is inside that control room. It's a pretty good way of thinking about it for now.
That is in the next container, and then to radio the bus driver to fetch that in.
The bus driver. Oh, geez, what's going on here? Pause it. All right, I don't know what happened there.
A program is stored in RAM and run by a CPU. The CPU is like a factory, and RAM is like the storage building connected to it. The storage building has numbered containers, all the same size and all in order, starting at 0. The factory also has some containers, each used for a special purpose.
This RAM.
A bus can travel between the buildings and move the content.
That was that lines of the lines. He calls it a bus. So he calls it a bus, but I mean, it's kind of, he uses this metaphor here of the bus, but that's when he's got the lines for all the data all lit up. That's what this thing is doing here. There's this little arrangement here.
Contents of any container into any other. Inside the factory, there is a control room where the boss works and a machine room where all the work gets done. As the factory owner, you tell the boss what to do. You load the storage building with instructions, one after the other, some with raw materials nearby. The boss cycles through the same 6-step checklist for every instruction and uses the clock to stay on pace.
This is the ALU. There's the flags. This is so funny.
The first item on the checklist says to make a note of the number that is in the next container, and then to radio the bus driver to fetch that instruction from storage. The second item on the boss's checklist gives the bus driver time to fetch that instruction and the boss a chance to make a note of it. The third item on the checklist says to add 1 to the number that's inside the next container, so the boss doesn't have to remember which container has the next instruction when this one is over. The 4th, 5th, and 6th items on the checklist are determined by the instruction itself. In this case, the 4th and 5th checklist items tell the boss to send the bus back out to the container that is next, container number 1 in this case, and move the raw materials inside into a container on the factory floor. The 6th item on the checklist, in this case, tells the boss to increment the number in the next
This is register.
container one more time, since this instruction used an extra container. Now the first instruction is over, and the boss starts the checklist again from the top. The boss makes a note of the number in the next container.
This is the instruction pointer. It says where it is, which instruction. There's only 11 instructions in this computer, 11 RAM spaces. There's only 11 spaces for RAM.
And then radios the bus driver to fetch that instruction from storage. The boss writes down that instruction, and then adds 1 to the number in the next container. This instruction is like the first, and it tells the boss to send the bus back.
There's 11 bytes of RAM. So each one of these things has an instruction or data or a parameter for the instruction, and it just collects them in. And you should go back and watch this, of course, without me blabbing over it. But that's what's going on. This is what kind of the high level thought process of the people who designed this digital circuit, with the way they were thinking about it. They're trying to get he's trying to help you the way we conceptualize it. It's not actually what's going on. It's just wires going but the way we're thinking about it, what with the process of kind of standardizing how we do this stuff. Yeah.
Back out to the container that is next, container number 3 in this case, and grab the raw materials from it and move them into another container on the factory floor. The boss again updates the number in the next container, adding 1 to it, since this instruction used an extra container, and then the cycle starts all over again. The third instruction sends the raw materials that are now on the factory floor to the machine room. To execute this instruction, the bus moves the raw material in the first container to the temp container. It then grabs the other raw material and parks next to the machine room. The machinist grabs bits from
So that's the input. That's the input on the ALU.
each raw material and gives them to the compare machine in this case, which tells him how their values compare. The machinist then raises a flag over in the control room telling the boss whether the materials
That's a flags register.
have the same value or if one is greater than the other. The flag stays up even after the instruction is over. The instruction cycle starts over, and the boss executes the next instruction, which says to first check if a particular flag is raised. The boss sees that the flag is raised, so the next part of the instruction applies. It says to put a new number in the next container. Normally, the boss updates the next container and just adds one to it as necessary. In this case, the instruction itself has an extra container with a number to put in that next container instead. The instruction
Right, so sets the instruction pointer. Right here's the instruction pointer.
ends and the cycle starts over again, except this time the boss will be executing an out-of-order instruction. That's how programming works. You write a long list of instructions that can handle any situation that may come up. You also frequently include some instructions to compare data values, and then jump to the appropriate set of instructions depending upon what situation the CPU finds itself in. In this case, all the data has been predetermined by the programmer, but normally a lot of that data comes from an external source like a user or a network. Find more at in1lesson.com.
That's how it works. Let me see what I'm doing here. Oh yeah, ALU. So this is how the ALU does the adding and subtracting. It's not a mystery. It's our friend Ben Eater. Oh man, he's so good. He's so patient for breaking this down like this. This is 13 minutes. You should go watch the whole thing, but I'm gonna skip through a little bit of it. But
so if we want to add 28 plus 22, it's pretty simple. 8 plus 2 is 10. So we put the 0 down here, carry the 1. 1 plus 2 is 5. It's 50. Okay, simple enough. Now if we want to do that with binary, it actually works pretty much the same way. So we line up all of our columns, and so 28 in binary is 11100, 22 is 10110, so we've got that converted. We line up the columns, we just go column by column. So 0 plus 0 is 0, 0 plus 1 is 1. 1 plus 1 in binary is 2, but we don't have 2 in binary, so
he went in here and converted these numbers to binary. This is the 1's place, the 2's place, 4's, 8's, 16's. And so everybody, where there's a digit, that's where he adds up. And now he's showing you how the math works with binary math.
Write it as 1, 0. So the same thing we did here with the 10. Here we do it the same thing. So we put a 0 down here and carry a 1. And that's how we write a 2. Here again, we've got 1 plus 1 plus.
That would set the carry flag in the ALU.
0, which is 2. So we write that in binary again by carrying the 1 and putting the 0 down here. And then finally, 1 plus 1 plus 1 is 3. And in binary, the 3 is 1, 1. And here we end up with the binary representation of 50. So the same algorithm works in any base, which is kind of cool. And so now if we want to build a...
Yeah, that was neat how that binary works the same way in all bases.
A circuit that does this for us. Really, it's actually a lot easier, I think, than regular arithmetic, because you only need to know a couple facts. And this is everything you need to know. And so if you can build a circuit that does all of this, then you can add a single column, because you've got the A and B, which is just the first number and the second number. And then you might also have this 1 that sort of carries in from the previous. So if you've got all that, then we should be able to add some numbers.
So that looks like just a basic digital circuit, just for one of these columns. For a single column here, these are all you need to know, all the rules for the binary addition. So you can see how people went like, oh, we can use this to do all kinds of stuff.
So let's think about how we would build a circuit that kind of does this. And one way to do it is just kind of break down inputs and outputs. So we have the inputs A and B, and then we have these 2 outputs, which are the sum that you put down here at the bottom, and then the carry. I'll call this the carry bit, because you would carry that bit over to the next column. So if we look just at the case here, where we've got 2 numbers that we're adding, so we haven't carried something in from a previous column, and we look just at the number that we're putting down at the bottom here, this actually looks a lot like an exclusive OR, right? Because if A or B is a 1, then this last bit here is a 1. If A or B is a 1, but not both.
Right, so exclusive OR is like an OR, but if it's both of them on, and then they flips it. So it's just another one of these Boolean logic things, exclusive OR. So it just happens to be a gate that we know, right, that how we can arrange some. We can arrange some of these basic and or not gates to do this XOR thing, which he's about to show you.
Right? So we can have an exclusive OR gate here. This is how you draw an exclusive OR. And we have our A and our B coming in. And then coming out is going to be this right here. Now what about the second bit, the carry bit here? Well, this is also pretty simple, because it's always going to be 0 unless A and B are 1. And so that's just an AND gate. So I can have an AND gate here. AND gate. And just take this same A and B input that we had over here, bring it into the AND gate, and this will be this bit here.
So you put the dots here. That means they're connected. They're soldered there. That's why I was giving the guy the animation a little hard time, because you do have to put those symbols there, and he does know better.
That we would potentially carry over into the next column.
It's important.
So this actually is enough to
you don't know what's connected or not.
This covers all of these cases here.
You'll see, it gets crazy. So he starts building all this stuff up, which you can go into if you need to go.
So this will...
If you want to see how he does it all step by step, you can go watch and see how he does it all step by step. But he builds this gate up from basically that, and then he just builds up the 4 of them for the 4 inputs, and It's basically just 4 copies of the same thing with a little carry thing. And then he says, here's a package, right? Here's some chips here that do the XOR.
And these chips here actually implement XOR gates.
So here they do just the XOR. And there's a symbol there for the XOR, the 2 inputs and the output. There's the function table, low, high, or means 0, 1. There's the Boolean logic function table. It's a truth table. They call it a function table. Okay.
Has 4.
So he builds this up, and then he puts it all together with a circuit with using those chips. Those are the chips. Those are the packages. And then there's the switches on the input for the A and B, and then he's gonna build it all up here. And
We'll try. So 10 is 1, 0, 1, 0. So we can do 1, 0, 1, 0. And already you see the output is 1, 0, 1, 0.
so you can go build that yourself if you want to see how it's put together. It's just a bunch of this stuff over and over and over and over again. And he's so patient. He puts it together for us. Now, you can go buy his kit and do it yourself to prove it, how it works. This actually is useful to know how this stuff works. But that's what he does. You can watch him do it. And if you do it with your hands, you will truly know how these things work.
Adding that
The
to 0.
bottom
So
level
10
is
plus
super
0 is 0.
useful.
So far, so good. And then 7, we can do 0, 1, 1, 1. So if we do 0, 1, 1, 1, there we go. We get 1, 0, 0, 0, 1.
So this is the value and the carry.
1, 0, 0, 0, 1. So it looks like it's working.
Yep. So that's how that works. And let's see, that is about it for this episode. We're going to be going to the configurable computer next. Thanks for watching. See you soon.